Okay, guys, so today we are going to be discussing the quotient rule for exponents. All right, we're also going to be talking about the power to a power rule. And lastly, we are going to be looking at negative exponents. All right, but first let's look at our quotient rule. All right, so that will be our first item to take care of on the notes. And the quotient rule says that when you have the same base, so when dividing the same base, we subtract the exponents. So very similar to our rule from earlier, when multiplying the same base, you add the exponent. Now we're going to be looking at examples when you have division. So there will be a fraction involved in each of these problems. And we're going to look at, again, the same base. All right, if it is the same base, you're going to subtract those exponents. Okay, so let's look at, say, x to the fifth over x to the third. All right, well, the reason why we can subtract these exponents and say that 5 minus 3 is x squared, all right, x squared over 1 or just x squared. All right, the reason that this works has to do with the idea of an exponent. So x to the fifth power actually means x times x times x times x times x 5 times. And x to the third power is x times x times x. Okay? And we know that the same number, like 2 over 2, is going to cancel out and just leave you with 1. So our x can cancel. I have 3 x's total that can cancel. We're just left with a 1 in the bottom, and we have x squared left in the top. And so for that reason, we have our quotient rule, which says that we can subtract those exponents when we are dividing by the same base. Okay, so let's look at a second example here. So let's say we have 2 over 3. Let's say it's x to the 10th over x to the 7th. And let's say y to the 4th over y to the 10th. All right, so for this one, we have several different bases. So you have a base of 2, you have a base of 3, you have a base of x, and you have a base of y. Okay, so for this one, we can only work with those that have the same base. So you have 2 over 3, there's nothing we can do to simplify that fraction. So we're going to have to leave this as 2 over 3. But now I can move on to this yellow highlighter base right here. All right, these x's. So I can look at 10 minus 7. I'm going to have x to the third left in the top or the numerator of this fraction. Okay, and for the y's, all right, I always start with the side or the either the numerator or the denominator. So either the top or the bottom, which one has more? And you would say, well, 10y's is definitely more than 4y's. So I'm going to start here and subtract 10 minus 4. All right, I'm not going to say 4 minus 10 because that would give me a negative exponent, which I haven't taught you how to deal with just yet. So we're going to say 10 minus 4, which is 6. And those 6 are going to be left in the bottom of the fraction because that's where they're going to be after you cancel out. All right, you're going to actually have variables left in the bottom for this case, all right, where there were some in the top for this case. So that's going to leave us with y to the 6th in the bottom of our fraction. So that's 2 examples of the quotient rule. We're looking at the same base, we're subtracting those exponents, and simplifying if necessary. Okay, let's look at our second piece for today's notes. All right, our second piece is what we're going to call the power to a power rule. Okay, so when raising a power to a power, all right, so when you have a power to a power, what you do with this is you are going to multiply your exponents. And we're going to look at a couple of examples for that. So what do I mean by power to a power? Well, let's look at, say, this example. All right, here's the first example for the power to a power rule. So let's say we have x to the 5th power, and that was raised to the 3rd power. Okay, so that means if we take our idea of an exponent, we have this thing in parentheses, which is multiplied by itself a total of 3 times. Okay, so I have x to the 5th times x to the 5th times x to the 5th. Okay, in this case, right here, the way this is written is really the same as our product rules, right? It's the same exact idea. You're multiplying the same base, and so you're going to add those exponents up. So 5 plus 5 plus 5 is going to give you x to the 15th, okay? But a shorter way, a way to skip from this step all the way through to this step here, is to just look at, hey, I can multiply these powers. 5 times 3 is 15. And so that's where the power to a power rule comes from. It's the ability for us to skip this step in the middle, which is writing out what that power is. And you say, well, why might I want to do that? Well, let's say you have x to the 3rd power, and it's raised to the 100th power. Well, I would not want to write out x to the 3rd 100 times. All right, would not want to do that. So we can use this power to a power rule to say that this is just going to be x to the 3 times 100, which is x to the 300th. This can also apply to whole numbers as well. So if we have 2 times x to the 5th power, and all of that's raised to the 4th power. Okay, this power on the outside, this 4, has got to go into both pieces. And I know we've talked about everything has an exponent, even if there is not one with that whole number. There's an understood 1 that is there. And so for this 4 is going to, it's kind of like being distributed in. We're going to multiply that 4 by the exponents there. So we're going to keep our base. The base is 2. 1 times 4 is 4. All right, the next base is x. 5 times 4 is 20. So this would be our answer for this one using the power to a power rule. All right, let's look at, let's say we have multiple rules here. So we have something all raised to the 3rd power. I have 2 over 3 x to the 2nd, y to the 3rd, all over x to the 5th. Okay? So I could, before I use the power to a power rule, I could simplify with the quotient rule right here and say 5 minus 2 is x to the 3rd power. Okay? That's one way of doing things. Or I could start with my power to a power rule and send this exponent in to each of the exponents in this problem. All right, on the top and on the bottom. And so what that would give us is we have 2 to the 3rd power because 1 times 3 is 3. We have x to the 2 times 3 is 6. And we have y to the 3 times 3 is 9. All over 3 to the 1 times 3, so that's 3 to the 3rd power. And x to the 5 times 3, which is the 15th power. Okay, so now we have a situation where in order to simplify, we need to use our quotient rule. which tells us to, when we have the same base, here the base is x, I can subtract these exponents from one another. So 15 minus 6, all right, sometimes I go on the side and just kind of use some scratch paper. All right, 15 minus 6 is 9. So this is going to leave me the simplified version of this. All right, everything else remains the same, y to the 9th, but I'm going to have my x to the 9th power, and that's going to have to remain in the bottom of my fraction because 15 is greater than our 6. Okay, so we've looked at the quotient rule, we've looked at the power to a power rule, and now we're going to look at the rule that deals with negative exponents. All right, so let's go to a new page here, and we're going to look at the third piece of our notes, which is negative exponents. Okay, and in order to do this, I'm going to show you guys a pattern and kind of where this rule comes from. So the rule for negative exponents, it says that if you have x raised to the negative a power, then we are going to say that is 1 over x to the positive a. So essentially, the negative exponent flips in the fraction. So flips in the fraction. Okay, and the reason why we use that rule and we say it that way is because of this pattern. So let's look at 2 to the third power, 2 to the second power, 2 to the first power, 2 to the 0 power, 2 to the negative 1, 2 to the negative 2. All right, so 2 to the third power is 2 times 2 times 2. Well, if we type that in our calculator, 2 times 2 times 2, we're going to get 8. Okay, 2 to the second power is 2 times 2. Well, 2 times 2 is 4. 2 to the first power is just 2, right? So that's going to give us 2. Okay, and now we have a case we haven't talked about, which is the 0 power, or 0 as an exponent. And we're going to examine this pattern and see kind of what's going on in order to get there. We began our year looking at patterns, and now patterns are coming back to help us right here in this situation. So how do I go from 8 to 4? Well, I'm dividing by 2, right? Dividing by 2. And 4, all right, to get to 2, I'm also dividing by 2. So for this pattern to hold true, I would need to take 2 divided by 2, which is going to give me 1. Okay? And so anything to the 0 power, all right, this is a good rule to write down. Anything to the 0 power is equal to 1. All right? Always, no matter what it is. It's always going to be equal to 1. Okay, and then using that divided by 2, 1 divided by 2 is 1/2, or 1 divided by 2. And you see that that is the same as 1 over 2 to the first power. These two fractions, 1 over 2 to the first power, is the same as 1 divided by 2. If you take 1/2 and you divide it by 2 in your calculator, you're going to get 0.25, which is the same as 1 over 4. And if you look at 1 over 4 by the negative exponent rule, since negative a is 1 over x to the positive a, well here, all right, it's negative 2, so that's going to be a 1 over 2 raised to the positive 2. And we know that 2 to the second power is 4. So our negative exponent rule tells us, okay, if we have, for example, this x to the negative 15 power, then the answer to that is just going to be 1 over x to the positive 15. Okay, and likewise, if we have a negative exponent in the bottom of our fraction, Okay, if we have it in the bottom of the fraction, it's going to flip up into the top of our fraction. So this would be 3x to the positive 3. Okay, over 1. You don't have to put the over 1, but we could. Okay, let's look at example 3, one that it applies multiple rules for us. So let's look at the following: x to the third power, x to the fifth power, y to the 10th, y to the third, all over x to the fourth, y to the third, z to the 10th, all of these raised to the -2 power. Okay, so what we need to do first is we need to distribute this power to a power rule to all of these exponents inside. So we're going to go through first 3 to the -2, that's going to give me x to the -6. 5 to the -2, that's x to the -10th. Okay, 10 to the -2, that's y to the -20th. 3 times -2, y to the -6. Okay, 4 to the -2, that's x to the -8. 3 to the -2, y to the -6. And 10 to the -2, that's going to be z to the -20th. Okay, so we have simplified this first part. And now we are going to go through and use one of our other rules. All right, so I would like to try to simplify the top and then do the quotient rule last if possible. So we're going to add our exponents together. So I have the base here is x and x. So -6 plus -10 is going to give me a -16. I have y to the -26. On the bottom, we have x to the -8, y to the -6, and z to the -20th. Okay, here we have negative exponents. So we need to flip every exponent that is negative and make it positive. So first, we're going to start with the -16. All right, that becomes x to the +16 in the bottom. Then we're going to look at y to the -26. That becomes y to the +26 in the bottom of our fraction. All right, x to the -8 in the bottom is going to become x to the +8 in the top. Y to the -6 in the bottom is going to become y to the +6 in the top. And then z to the -20 is going to become z to the +20 in the top. Okay, so last step for us is to look at our quotient rule. And I see that I have a couple of bases that are the same. All right, I have x and I have y. Z is a base by itself. So I can, when the bases are the same and we are dividing those bases, I can subtract the exponents. So starting with x, 16 minus 8 is going to give me a x to the 8th. It stays in the bottom because 16 is larger than 8. For the y's, the base of y, 26 minus 6 is 20. So that's y to the 20th. This stays in the denominator or the bottom of this fraction because 26 is greater than 6. And then lastly, we have our base of z, and z is raised to the 20th power. There is nothing left to simplify on that. So this is a good example of where you might have to use all 3 of your rules. You may have to use all 4, right? So different problems call for different rules, but those rules can be combined in order to fully simplify